So we are moving on through my 5 types of reactions. We're now on our 4th type of reaction, which is a double replacement reaction. And you will know you have a double replacement reaction coming when on your reactant side you have 2 couples. The only option for them is to switch partners in some way to create 2 new couples. This was the wife swap TV show example here. We will also be using what's called our solubility rules. In my class on the back of our periodic table, we have a list of the solubility rules, and we will totally start practicing how to read that today. So a double replacement reaction is a reaction where 2 compounds react to form 2 different compounds. The key thing about my double replacement reactions is these are ionic couples. Okay? So if I'm doing ionic stuff, maybe to write the formulas for all of these ionic compounds, I'm going to be dealing with crisscross. Y'all are like, oh my gosh, this is never going away. It's not. It's not. I'm sorry. So I'm going to zoom in here a little bit. Okay, I've got my red and blue colored pencil. So each one of these ionic compounds, if you'll notice, the red metal is always written first, and the blue nonmetal or the blue anion of some sorts, because it could be a polyatomic ion, is written second. So there is some strategy involved when you decide to flip couples that you make sure after the couple flipping you do not have 2 blue things together and do not have 2 red things together. Everybody gets a blue thing and a red thing, and that red thing needs to be written first. I love how I just say thing, like I do not know chemistry. The red ion needs to be written first. The cool thing about these double replacement reactions are a lot of them are precipitation reactions, which is why we use this solubility rules chart. So specifically, all of these double replacement reactions we're going to be doing are either going to be precipitation reactions or acid-base neutralization reactions. So let's look at my solubility rules chart, and I actually think I just kind of want to look at the slide because I feel like this is a little bit more clear. So we know a precipitate is an insoluble compound that's formed by me mixing 2 aqueous solutions of ionic compounds. Usually these precipitates are super bright colors, kind of shocking, but they're solids that are eventually going to fall down to the bottom of the beaker or the reaction vessel. That's because those ionic compounds that I'm forming from a double replacement reaction are not soluble, which means they do not want to comfortably exist as ions free floating in solution. So what does this mean to me? So I notice on my activity series, that was single replacement. I've noticed on my solubility rules chart, it's broken up into 2 halves. This top half represents compounds that are soluble, okay? If I'm soluble in water, I'm floating around as ions. I've dissociated, okay? If I am down here, I am insoluble. That means they are not existing as ions. That is a precipitate. So these are your precipitates down here. We would write a solid after their formula to indicate that that precipitate is not existing as ions in solution. Very cool, very fun. There is some strategy involved in like finding your compound on there, and we will practice when we get into certain examples. But I thought I would mention that right now. So I thought maybe we could also then document what I just talked at you about on our page. Okay, that down here on my insoluble category, so these are solids, okay? So they are insoluble. And this is where my precipitate is formed. So my precipitate is down here. So in those precipitation reactions, one of the products of a double replacement will be a solid precipitate. The other one will be soluble. And if something is soluble, or an ionic compound is soluble in water, we will say it is aqueous, right? So aqueous is soluble. So let me show you an example of what that looks like down here, okay? And I think my PowerPoint slide kind of scaffolds that or models that in some way. Yes. Okay, so looking at these precipitation reactions, it says 2 aqueous solutions of ionic compounds react to form a precipitate, or a compound that is insoluble according to my solubility rules. So looking at this, I have lithium bromide and silver nitrate. On my specific example on my page, what I want y'all to notice is I wrote aqueous, aqueous after those two reactants. That's because these ionic compounds need to be dissolved in water as free-floating ions. I also noticed that each one has a cation metal and an anion nonmetal. Do not be afraid. Nitrate, he's totally a anion polyatomic ion, right? So he'd be blue. He'd be blue. And then they swap partners, yes, to where I make a new couple between lithium and nitrate and another couple between silver and bromine. Please, please, please notice that I've got a red and a blue on my products, each one of those, right? Please, please, please notice that the red metal cation is written first. Now, what's interesting, though, is that I can look for each one of these products on my solubility rules, you guys, and see where they will fall. If I'm trying to identify lithium nitride, and I'll look at the one on my PowerPoint slide, usually I find them first based on the anion. The anion classification is what is written on this chart. And then there's a section over here that if there are any exceptions. Let me be clear about the exceptions. If you find yourself in an exception to what that compound normally would be, that means you are in the opposite chart category. Let's just look at lithium nitrate. So I'm saying nitrate, 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 nitrate. I see nitrates. Nitrates are all soluble because there are no exceptions. So lithium nitrate, totally. I've written here on my note page, I put aqueous. He's soluble. He's going to exist as ions, yeah? But now if I try to find silver bromide, does everybody see here on my solubility rules halides? You're like, what does that mean? That just means the halogens that are in an ionic compound. Bromine is totally a halogen. So bromine's a halide. You're like, cool, he's soluble, except look who is an exception if it is paired with one of my halides. Silver. So most bromides would be soluble, but if they be paired with silver or, lead or mercury, boom, now I am insoluble, which is why you see that S right there, okay? So I've identified who my precipitate is. Okay, so my precipitate was in the insoluble category, which we love. So most of my double replacement reactions that we'll be doing are my precipitation reactions, where I will be using the solubility rules. Another common double replacement reaction is what's called an acid-base neutralization reaction, okay? An acid-base neutralization is where you have a strong acid and a strong base react to form a salt, which is any ionic compound, and water. So here I have a solution of lithium hydroxide and hydrobromic acid. My lithium hydroxide is a base. For our intro, we're not even in the acids and bases unit until way to the end of next semester. But if you see something that has a metal and hydroxide, these are your bases, okay? And then I mix it with an acid, which is anything that starts with hydrogen, right? And is paired up with a nonmetal anion. If they swap partners, look guys, I just make an ionic compound between a metal cation and a nonmetal anion. Very boring. That's a salt. But look what else I make for my other product. I make HOH. I've created water here, okay? And water is a liquid. You do not have to be like, oh gosh, how am I going to remember which is a base? These will, if you are just swapping partners, these will naturally appear to you. I just wanted to show you an example where, yeah, you can form water, and I'm not going to be having to look at my precipitation reactions solubility rules for that. So there are a few examples in here where I have you swap partners and you have that acid-base neutralization. Okay, so my example here was we had my lithium hydroxide. I put my hydroxide in parentheses so I can more clearly see him as just the anion. Not a big deal. We like him, right? And we're swapping partners with my hydrobromic acid to where I get a salt of lithium, bromide, and my water, who is acting like an ionic compound between hydrogen and hydroxide. Yes, so I've got precipitation reactions, which most of our practice will be because they're fun to read the solubility rules, and then my acid-base neutralization reaction where I produce water. So we will label this base, we will label this acid, we will label this salt, and this is our water. Yeah, okay, so now we're going to bounce down to the document camera, and we're going to see if we can do some of these reactions, okay? This is super fun. We are ionics. We are crisscross, yes? I'm going to have us write this on everything because it is super important. Do not bring subscripts over from the reactant side. So don't bring over, you could not see any of that, over reactant subscripts. When I'm forming new couples with new partners, I'm not bringing my baggage from my previous relationships into new relationships, right? I leave that baggage, those subscripts behind and figure out what new subscripts I need according to the ionic crisscross. Okay. Oh, we are ready to go. I am super excited. Okay. Since these are all ionic compounds, I should see in each one of my couples two things. If it looks like more than 2 letters of the alphabet, congratulations, you have a polyatomic ion. Put some parentheses around there because we know we're going to have to balance these, and that might be helpful for me to where I can, on this first example, more easily see sodium and copper being my metal cations, and my hydroxide polyatomic ion and sulfate polyatomic ion being the anion components of these ionic compounds. Great. So now we're going to swap partners. This is where y'all screw up a little bit. Make sure in the new partners you have one red and one blue, and make sure that the red is written first. So that means sodium is totally going to try to pair up with my sulfate. And my hydroxide is totally going to pair up with my copper. So writing the formulas for these things is I'm going to crisscross to figure out what ratio I need to each one of these ions, okay? I'm not going to take the time to set up my crisscross for every single one of these compounds because I'm going to be writing a lot of them, but it may be helpful to remind yourself that, hey, sodium, he's a group 1 guy, he's got a +1 charge. Hydroxide on my polyatomic ion list has a -1 charge. Copper, oh, he's a transition metal. We'll come back to copper later because we'll write his couple between copper and hydroxide second. But I do know sulfate's charge. Sulfate is my polyatomic ion, and he has totally got a -2 charge. So what that means is when I'm grabbing my sodium and my sulfate together, I've got the charges already identified there. Boom, right? So that means my formula for sodium sulfate is going to be Na2SO4. Awesome. Now let's focus on that second guy. That second guy is between copper and hydroxide. I know I have to write the copper first, and we know hydroxide's charge is a -1. What charge does copper have coming to the table? He's a transition metal. I don't know, based on his group, what his charge is. He could have lots. Well, I got look. Here's him in another couple. We can look at what the ratio of those two ions to each other, figure out what his original charge is. Well, if he's paired up with sulfate, who has a -2 charge, and it is a 1-to-1 ratio of the red thing and a blue thing, that means that copper has to have a +2 charge. So forming the couple between copper and hydroxide, I'm going to have a 2-to-1 ratio, okay? But who gets written first? The copper gets written first, and the hydroxide is second, right? So the copper with the +2 charge, I only need one of him to neutralize or cancel out the -1 or 2 of the hydroxides with a -2 charge. Great, lots of stuff going on in there. Okay, and if you want, you can totally check to make sure that you have one red thing and one blue thing in each one of your new couples that you formed, and it looks like I have done that. But I'm not ready to walk away. I know I have to balance at the end, so let's get some of this balancing done. I'm super excited. Okay, balancing. I got 2 sodiums on the product side, so I might want to put a 2 in front of NaOH, which then that gives me 2 hydroxides. But we're good there, and I think everybody else looks good to me. Yes, parentheses around polyatomics. We know that is so helpful in balancing. Thank goodness for that. All right, but this is a precipitation reaction, okay? Now I have to figure out, well, which one of these 2 ionic compounds is in my insoluble category according to my solubility rules. So let's get these guys up here. Okay, my first compound is sodium sulfate. Sulfate. Where are my sulfates? Oh, looks like most sulfates are soluble. Is sodium an exception? No, there are some exceptions, but sodium is not one of them. So that means yes, sodium sulfate is soluble. He's not my precipitate, okay? Let's see if copper hydroxide is. Let's see, hydroxide. Oh, whoa, okay. Looking insoluble to me. Is copper an exception? No. If he was an exception, that means he would be soluble and not my precipitate. But I am totally insoluble. He is a solid. So I can identify this as my precipitate by just putting an S at the end of the formula. Or if I were to ask you which one is the precipitate, you could tell. A lot of kids are like, I don't know, all these words, soluble, solid, insoluble, aqueous, precipitate. If you want to kind of visualize your solubility rules as like a beaker, okay, we know an insoluble solid precipitate will eventually fall down to the bottom of the beaker. So that helps me kind of visualize that my insoluble guys are, they're going to be my precipitates, if that is helpful to you. Okay. We're definitely not going to do all of these examples because this is a lot of formula writing for me. I'm going to do a couple more from this section where I've given you the reactant formulas. And then we're going to do a few towards the end of the back page where you won't have to write all my formulas for me. Ooh, this is fun. Okay, I'm excited. Okay. So let's see here. Lots of letters of the alphabet. They are all ionic compounds. Find your two things. We got polyatomic ions, if that helps. I got ammonium, who is my only positively charged polyatomic. Let's see if I have a red thing and a blue thing. Yep, ammonia. With your +1 charge. There you go. Iodine, non-metal, right? Silver, a metal. Nitrate, a non-metal. Looks good to me. So it looks like ammonium, red ammonium is going to pair up with nitrate. Yes? Do not bring any previous subscripts over. Okay, I make my own subscripts when I make my new relationship, right? So it may be helpful just to remind yourself that ammonium has a +1 charge and nitrate has a -1 charge. So when I make that new formula between these two guys, not only is my ammonium going to be written first and my nitrate second, but it will be a 1-to-1 ratio of those ions to each other. So I have, and I'll keep them in parentheses because I know I'm about to balance and this may be useful for me. It will be useful for you. Cool. It's my first couple. My second couple is between silver, who silver always has a +1 charge, and iodide. Iodide is iodine. He is a halogen, always has a -1 charge. Cool for that. Okay. Another 1-to-1 ratio we got going on here. So we have AgI. Amazing. Balancing. Everybody is balanced. We got ones of everybody. This must be a precipitation reaction if I have given you just 2 ionic compounds. Let's check the chart and see who is going to be at the bottom of the beaker, my solid precipitate. Let's start with ammonium nitrate. Nitrate. Oh yeah, all nitrates are soluble. So yeah, you're not a precipitate. What about silver iodide? Iodide. Now remember, my halogens are my iodides, bromides, fluorides. So I have this category of halides, which, yeah, that's where, what halide am I dealing with? Iodine. That's where iodine is. You're like, cool, he's soluble too. But look who is an exception. Silver is an exception. So that means although most halogens are soluble, if they are paired up with silver, I am now dropped down to the bottom of the beaker. This guy will be your precipitate. So since these are our examples for our notes, if you want to write, these are your precipitates. Okay, amazing. Let's do, what do I want to do? Let's see. I am going to do, let's flip to the back and do number 4 and then number 5. That's what we're going to do. So number 4, okay, I got 2 couples, so I know I'm going to be doing a double replacement reaction. Find the 2 people in your compounds. Yep. Identify who is the metal and cation and who's the non-metal anion. Okay. That means copper is going to pair up with carbonate. Uh-oh, I got to figure out what the charge is on this copper, right? I do know that carbonate has a -2 charge. Copper. Well, according to who he is in this formula with bromine, we know bromine has to have a -1 charge. He's a halogen. So that means that copper has a +2 charge. I needed only 1 of that positively 2 charged copper to neutralize 2 of those negatively 1 charged bromines. So I've got copper 2. So that means copper with a +2 charge, when he mixes up with carbonate with a -2 charge, that is a 1-to-1 ratio to make copper 2 carbonate. Amazing. So that's my first couple. My second couple is between the bromine and the lithium. Yes, the bromine and the lithium, but I gotta make sure I put the lithium first because he's my positive guy. Lithium's group 1, always +1. Bromine, we said he had a -1 charge. So this is a 1-to-1 ratio of those ions to each other, with the lithium written first and the bromine second. Cool. There is some balancing that's required, which is why I did not bring that sneaky 2 that was underneath the lithium over here. That is baggage from a previous relationship. Do not bring that over. Okay, well, that means for my balancing, I need to figure out how I can get 2 lithiums on this side. Well, I put a 2 in front of lithium bromide, which changes the number of bromines on the product side to also be 2, which means I be good there. Okay, I made 2 ionic compounds. I made 2 salts. Who's soluble and who is insoluble? Who is my precipitate? So I got a copper carbonate. Carbonate, 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 carbonate. Oh, wow, carbonates are insoluble. Is copper an exception to that? No, I do have a few exceptions, but copper is not. And if I'm not an exception, I stay in my category. I'm at the bottom of the beaker. I am my solid precipitate. So this is your precipitate. And I will always only have 1 solid precipitate. The other one will be aqueous, but since we're practicing using our solubility rules, it might be a great idea to just check and see if we can find lithium bromide on there. Bromide, that's a halide. He's a halogen, right? Halides are all soluble unless you are these 3, and lithium is not included in the exceptions. So yeah, he's totally soluble, okay? He will not be a precipitate. Good to know. We're going to do number 5, okay? And then we're going to bounce on down where I have to write all my formulas for all my things. Okay, number 5. Ooh, polyatomics. Let's get it done, get it done, get it done. I have got my red things, potassium and the hydrogen. I'm like, oh, hydrogen, hi, this is an acid, right? And if you remember from when we first started this lesson, I mentioned that metals, when paired up with hydroxide, we call those typically bases. Regardless, we're just going to do what we know to do and swap partners, and we'll see that maybe this is an acid-base neutralization reaction where we make water. Let's check it out. Okay, what charges does everybody have that I need to be aware of? So potassium is now going to pair up with iodide. Potassium's group 1 with a +1 charge. Iodide is group 17 with a -1. So my formula for potassium iodide is Ki. Yep. And then my second ionic compound is going to be between hydrogen and an acid. He acts like a cation with a +1 charge. And then hydroxide polyatomic always has a -1 charge. Another 1-to-1 ratio. Making sure that I write the red cation first. Okay? Ready to balance? Everybody's already balanced. I feel good about that. But you guys, look what I made here. I made water. So here I've got my base and my acid neutralizing each other to make a salt, which is an ionic compound, and water. So I like to put a little liquid symbol next to my water to remind myself that this is an acid-base reaction. All right. I want to do a few from the writing all of our own formulas thing. Let's see which ones I want to do. I want to do numbers 7. Yep, we'll start with 7, and then we'll do 10 and 12. I'm going to star those to remind myself what it was that I just said. We're going to do 7, we're going to do 10, and then we're going to do 12. Which will leave you guys a great sampling to do completely on your own because we are all so smart now. Okay, ammonium sulfate. You're like, oh my gosh. You guys, do not worry. Each one of these things is a red thing first and a blue thing second. They may be polyatomic ions. That is fine. Ammonium. What does ammonium look like? He is my only positively charged polyatomic, right? So if you want to remind yourself that ammonium's got a +1 charge. Sulfate is also a polyatomic. He's a negatively charged polyatomic. So I'm just writing these up here because it's nice to visually see what all of that mess is going on inside of that polyatomic. Plain old barium, he's just barium from the periodic table, group 2 with a +2 charge. And plain old chlorine, that's chlorine from the periodic table with a -1 charge. I'm not going to take the time to write the Ba and the Cl and stuff, even though that wouldn't take much time, but it's whatever. Okay, so writing the formulas for ammonium sulfate, I have 2 ammoniums and 1 sulfate. Got a 2-to-1 ratio of those ions to each other according to their charges. And then for my barium chloride, okay, it's going to be BaCl2, a 1-to-2 ratio of those guys. So now I'm going to have them swap partners, and if you still want to use your reds and blues, that is helpful so you can make sure that you don't accidentally put two blue things together or two red things together. Ammonium is now going to pair up, not anymore with sulfate, but with chlorine, okay? We mentioned that chlorine has a -1 charge. Ammonium still got his +1 charge. So with making ammonium chloride, it's going to be one of each one of those ions. Yep. And then making my new couple between sulfate and barium. The barium has to be written first. Barium's charge is a +2. Sulfate's charge is a -2, so that will be a 1-to-1 ratio of those ions according to their charges, with the barium written first. Noticing I'm keeping the parentheses around my polyatomics because now you guys, I got balance, right? What I noticed first is my ammonium. I got 2 on the reactant side, so how about I put a 2 in front of ammonium chloride on the product side, which then gives me 2 chlorine. I'm good. We good. Exciting. Well, I made 2 ionic compounds. Which one is your precipitate? Let's see. I got ammonium chloride. Chloride is a halide. Oh, they're all soluble, and ammonium's not an exception, so he's not a precipitate. But what about barium sulfate? Barium sulfate. Those are also soluble, but barium is an exception to where most sulfates are soluble. Barium sulfate is not, and he will be insoluble. He is your solid precipitate. Cool. Okay, moving on down. I love number 10. Number 10 is a good one, I can tell. So I've got iron 3 chloride and barium hydroxide. Yep. So that 3 Roman numeral behind the iron is not that I have 3 irons. He's got a +3 charge, right? Chlorine is plain, or chloride is plain old chlorine. He's got a -1 charge. Barium is plain old barium again. He's got a +2 charge. And hydroxide is a polyatomic ion. He is OH with a -1. So I have all my players here. I know their charges to where when I make all their couples, I can real easily see what it is that I'm assembling here. So iron 3 chloride, the formula for iron 3 chloride is going to be FeCl3. And then the formula for barium hydroxide is going to be BaOH2. And if I'm breezing way too fast on creating these formulas and you're like, where is she going? Go way back to Unit 5 on writing ionic nomenclature. We got, this is a big process, so I am not going to take the time to set up the crisscross and explain every single one of those. I'm hoping that at this point y'all are tracking me a little bit and able to write some ionic formulas. Okay, cool. Make new couples. Drop the subscripts. I do not care. Get rid of them. Start a fresh crisscross on how many of each ion you need for my new couples that I'm trying to form. My new couple is going to be between iron 3 and my hydroxide. Looking at their charges of a +3 and a -1 charge, iron 3 hydroxide is going to be FeOH3. Yep. And then my second couple is going to be between barium and chlorine, with the barium metal cation written first. Since he has a +2 charge to chlorine's -1 charge, my formula is going to be BaCl2. 2 ionic compounds. Who is my precipitate? Who is at the bottom of my solubility rules chart? I've got hydroxide, iron 3 hydroxide. My hydroxides are insoluble. Iron is not an exception to that, so I totally have iron 3 hydroxide as my solid precipitate. Just checking my barium chloride to exercise reading my solubility rules. Remember, chlorides are a halogen or a halide, right? Halides are all soluble, and barium is not an exception to that, so we are not a precipitate on barium chloride. Awesome. Last one I want to do, super fun one. Sulfuric acid, acid. To write a formula for an acid, it is a crisscross always between hydrogen with a +1 charge and whatever the anion is according to the name. If it does not start with hydro, I am dealing with one of my negatively charged polyatomic ions. If the ending of the acid is ick, I ate something icky, which means the original polyatomic ion ended in 8. So I've got sulfate. So my crisscross is between hydrogen with a +1 charge and sulfate with a -2 charge. So my formula for sulfuric acid is H2SO4. Amazing. Wait a second, y'all. I did not balance. I did not balance my problem number 10. Get it together, Sabaka. Okay, we got to do some balancing, don't we? Okay, let's see. Who is not balanced here? Wow, I'm looking at hydroxides already. I'm like, that's going to be a problem if I have 3 on one side and 2 are on another. How about we even odd, double the odd to kind of get us out of that weird zone? So I'm going to double the side where hydroxide has a 3. Yes, that gives me now 6 hydroxides. I can fix that over here by putting a 3 in front of barium hydroxide to get 6 hydroxide on the reactant side. Well, now what have I done? That is okay. Let's maybe make 3 bariums on this side. Well, now I've got 6 chlorines. Yes, you do. And that means I can put a 2 over here in front of iron 3 chloride to get the 6. And yeah, we balanced now. Okay, I'm so glad I did not forget to balance. Did I forget to balance any of the other ones? No, I think I've done a good job for myself so far. But yes, do not forget to balance, which is why I put the blanks there. So you don't forget, like I just did. And even when I put the blanks, it sometimes happens. We're all imperfect people, and we can do the hard things. Okay, so I got my sulfuric acid back to number 12, yes? Then I've got lithium hydroxide. Plain old lithium, a group 1 metal, +1 charge. Hydroxide, polyatomic ion. Ooh, it looks like I got an acid and a base. I bet this is going to be a neutralization reaction where I maybe will make HOH water. We'll have to see. Okay, so my formula, though, for lithium hydroxide, if it's a 1-to-1 ratio, will be LiOH. Cool, cool, cool. Swapping some partners, and if you needed your pencil for your reds and your blues, for your cations and your anions, that means my hydrogen cation is going to pair up with the hydroxide anion. Do not bring subscripts over, right? We know what charges they have. We just need to know what ratio of those ions you need with each other, right? So I have hydrogen and hydroxide, right? HOH. 1-to-1 of each one of those. There's your water. Yes? Like water, liquid water. And then my salt, or my ionic compound that I'm going to be making, is between the sulfate and the lithium, with the lithium written first. Noticing that lithium has a +1 charge and sulfate has a -2 charge, that will allow me to know the ratio is Li2SO4. Okay, so I'm keeping those parentheses because I know that'll help with my balancing. We are ready to balance. I am super excited. So balancing, I'm looking at my hydrogens outside of OH. I've got 2 of them on the reactant side. So how about I put a 2 in front of my HOH water? Well, that gives me now 2 hydroxides. Well, how about I put a 2 in front of lithium hydroxide? Well, that gives me 2 lithiums. Yeah, we have 2 over there. So we look balanced. So that is great stuff. So this was double replacement reactions. Double replacement reactions where everybody be swapping partners. They are either, at least for the case of this intro to chemistry course, they're going to be precipitation reactions. If I get 2 ionic compounds formed from the swippity swappity, then I'll be reading my solubility rules chart and seeing which one falls down here at the bottom as the solid precipitate. Or if they're an acid-base neutralization reaction, I'll be making water from that in the neutralization of an acid and a base. The key things here on my double replacements, on my crisscross, because they're all ionic compounds, and this ongoing thing of do not bring the baggage subscripts on my reactant side over onto the products. You must create brand new formulas according to what the ions are that you are now trying to join together to make these new compounds.